Okay. Um, so the first question is, what are the Einstein coefficients primarily used for in the field of quantum mechanics? So I want it to be interactive. So you can answer the question. 4 options are given. You read this and give me an answer.
Option B.
Yes, right. Einstein coefficient primarily used for describing the interaction between matter and electromagnetic radiation. Right. Okay, the next question is, which Einstein coefficient represents the rate of spontaneous emission? So here are the options. Tell me the answer. Hello.
Option B. Option A.
Option, which option?
Or uh, B coefficient.
No. Yes,
No.
not stimulated, it's spontaneous. So this B means, according to class, let me write it down. This is B12, B prime is B21. Okay. So if there are two level systems, let it be state 1 and this is state 2, then when a photon is coming and hitting the electron in this state 1, then this electron will gain energy and go to the next state. So this transition is called absorption, right? So this transition is described by Einstein coefficient B12 because it's going from 1 to 2, right? This is this is stimulated actually due to presence of external radiation. This transition is happening, so this is stimulated. So one more thing can also happen. When this electron is in second state, one photon can come and stimulate this photon to go to ground state, then it will radiate one photon and the incoming photon, they'll be emitted together, right? So this is stimulated by this external radiation, so this is called stimulated emission. This is described by Einstein coefficient B21 because it's going from 2 to 1. Okay, so these two are in the presence of radiation, external radiation. Now let's assume there are no external radiation. Your system is in a closed box where there is no external radiation. So in that case also, this electron from second state can come to the first state spontaneously. You don't have to give any external energy. It will come to the ground state spontaneously and emit one photon. This kind of process is called spontaneous emission. This is described by the Einstein coefficient A to 1 or simply just A. So the correct answer is this C. Okay, so these all are taught in class in week 4. Okay, so any doubts?
No, sir. It's
Okay. Okay, then we will move to the next question. What is the primary difference between Einstein coefficient A and B? Then, so these are the options. Tell me the answer. Just now I told you what A and B coefficients are.
option C.
Yes, correct. Option C. A is spontaneous emission and B is simulated emission. Actually, you see, this both absorption and stimulated emission, they are happening in the presence of this external radiation. So from that we can interpret that these constants are same. Actually, this is taught in class. So this B12 will be B21, and we are calling this parameter as B, right? So this B describes absorption and stimulated emission, where this A describes the spontaneous emission. Okay. Okay, then coming to the next question. What is the rate of spontaneous emission calculated using Einstein coefficient A? Hello? Any guess? This is being taught in week 4. So this, let me tell you what is N1 and N2. If there are two states, then in first state, then population density is called N1, and in second state, the number of particles is called N2, right? So
So it's option B. No?
yes, right, because it's spontaneous emission, so it will come from excited state to ground state, so it will depend on the number of particles in excited state. Okay, and it will depend on this A coefficient, but how they will depend, they will be dependent. Actually this emission is happening, right? So the rate of change of this N2 number, we can write minus dN2 over dt equal to A N2, right? Where this A is Einstein coefficient, or you can call it as decay constant in this case. So this is the rate of spontaneous emission. Okay, which is given as A N2. So this B is the correct answer. Okay. Okay, coming to the next question. What do Einstein's coefficient help explaining in the context of absorption and emission spectra?
Option C, sir.
Yes, right. Good. So this Einstein coefficients, they help explaining the probabilities of absorption and emission process. Right. Okay. Coming to the next question. How do Einstein coefficient provide insight into astrophysical phenomena such as the study of stars? So these are the options.
Sir, is it B or C?
This is C.
C.
What Einstein coefficient explain? This explains absorption and emission process, right? So it can't means by using this we can search for the molecules or atom present in cosmos. So the correct answer should be this C. Explaining formation of galaxy, I don't think the Einstein coefficient is used. So this is a dynamical process, and here in interpretation of emission line and absorption line, this this is the primary aim of this Einstein coefficient, right? So by observing cosmos, we are always bombarded with cosmic radiation, right? So from distant stars and galaxies we are getting light. So by studying this light we can find um, the emission lines and absorption lines, and from that we can determine the star's composition. Okay, so if there is some uh, dust cloud in universe and light is coming from this, passing through this dust cloud, so um, this dust cloud is mainly composed of uh, one second, hydrogen gas. So if you observe this light which is coming through this gas, then you will notice one dark page which is called absorption spectra. From that you can identify there are hydrogen in that in this universe, or in this dust cloud is composed of hydrogen. Okay. Okay, coming to the next question. um, what key assumption is often made when applying Einstein coefficient to real world atomic and molecular system? So these are the options.
Sir, option C, sir.
Yes, right. Options. Normally when we consider this Einstein coefficient, we consider absorption or emission between two states, right? So C. Good. Okay. Next one is the problem. In two level system, the molecule is in first excited state and spontaneously transition to its ground state. Calculate the rate of spontaneous emission using Einstein coefficient A, and assume that the n is this 10 to the 15 molecules in this excited state given A. Okay, so what do you have to calculate? The rate of spontaneous emission. Just now I told you here, this one, rate of spontaneous emission is equal to A N2. So it's pretty straightforward. You are given A, you are given N, and in state 2 these many molecules are in excited state. That means state 2 is populated by this N. Okay, are you getting it? Or you can picture it as if there is one molecule.
Yes.
Yeah, and that electron is in second state. There are n such states. Okay, n such molecules where this electron is in second state. Okay, that's process is same. Just you have to multiply A and N, then give me the answer, multiply this and tell me the rate.
6.27 to the 22 per second.
Unit
Per second.
second, right? Okay, good. Okay, coming to the next question. Examine how this A and B coefficient depends on length of one-dimensional square wave for the transition n to n minus 1. Okay, so this potential is one-dimensional square wave and there are many states and starting from 1 to n and so on. Okay, so you have to we have that this particle is making transition from n to n minus 1. Okay, so in this case how this A and B coefficient will depend on the length of the square wave. So any idea?
No, sir, discuss. No, sir, discuss.
Okay. So we have learned that this Einstein coefficients A and B depends on this what you call this moment. Once again, yeah, we call this A and B coefficients, they depend on this transition moment integrals. This transition moment integral mu dot E, they depend on this. Okay, okay, these are called transition moment integral. Okay, so our one state is n state and two state is n minus 1 state. Okay, so what are these states? These states are nothing but the wave function in that particular state. Okay, so we know the general wave function for one dimensional potential. This is nothing but 2 over L root over sine for nth state n pi x over L, right? So similarly psi n minus 1 will be 2 over L root over sine n minus 1 pi x over L. Okay, okay, what is this moment? If there is a molecule A and B, so it will be composed of this positive and negative charge, right? So then it will have a direction moment, electric moment, right? Then it will depend on charge times the distance between these molecules. Let's say this is R. Okay, so charge is, let's say, E and distance is R. Okay, then in that case mu can be written as E times or minus E if we are considering electron, E times R. Okay, and it will be dot product with this external electric field. Right, this is external. Let's assume this molecule is aligned with this external electric field. This is unit vector, so its magnitude is 1. This is external electric field, so the dot product of these two will give us minus E dot R, sorry, this not dot product, ER times 1, and cos theta. Theta is same direction, let's say cos 0, then it's 1. So this term is giving us minus E times R. Okay, so in quantum mechanics, you know this R is your operator, or in this case, let's say this is in x direction, then this is minus E x. Okay, so you have mu dot E as minus E x. Okay, now you have to evaluate this, and mu dot E n minus 1. Okay, this is the final state, so it's n minus 1, then here n actually n minus 1 n. Okay, so you have this minus E x, and you have this wave function, and you have also this wave function. What you have to do? You have to do this integration 0 to L, because the potential is only from 0 to L. In other limits it will be 0. So you have to write psi n minus 1 star minus Ex psi n dx. Okay, so you have to evaluate this first. Then from class you must know the B coefficient. It will be equal to this will be equal to pi over 6 epsilon naught h cross square mod of this integral n minus 1 mu dot epsilon n square. Okay, so first you have to evaluate this, then you will get B. Okay, then if you get B, then from the class we know A by B will have some form like 8 by h over CQ nu q, where this nu is the frequency. So we will use this relation to get A. Then first we have to find B. Okay, how we will get B? From this integration. So this integration first you have to do, then if you do, then it's pretty straightforward. And how do you calculate this nu? Any idea? This is a one-dimensional potential wall. How do you calculate this nu when the energy transition is from n to n minus 1? What is the energy of nth level?
H nu.
Sorry.
H H cut nu.
This is H nu. Okay. And for 1D potential world, what is the formula for En in terms of this potential wavelength? We have been doing this last 3 classes, so you must know this. This is n square h square by 8 ml square, right? En, and this is not h nu. H nu is the energy of light, whatever external photon we will provide. So this external photon h nu, let's say this is a stimulated emission. This photon will come h nu. This will stimulate on this electron or particle in this nth state to go to this n minus 1 state. So it will emit this h nu, and there is also h. Okay, so this is the energy of external photon, or you say this is the emitted photon energy. Okay, so this should be equal to the energy difference, right? This is En, this is En minus 1. So h nu should be En minus 1, right? From this I will get h nu. If I get h nu, from that I will get nu also, En minus 1 by h, right? So you have the formula. Then tell me quickly what is this numerator will be. Okay, En is what? N square h square by 8 ml square, right? Then En minus 1 will be n minus 1 square h square by 8 ml square, right? And in denominator we will have this h. So I can take all the common factors out. Then this will be n square minus n minus 1 square times h square by 8 ml square by 1 over h, right? Now can you solve this? It's very pretty simple. Just tell me on this number.
2n minus 1.
Right. N square will cancel and 2n minus 1 will remain. Okay. So nu we got 2n minus 1 h over 8 ml square, right? So we got nu. But our first task is to evaluate this integration. So you have psi n and psi n minus 1, right? You have to do this integration from 0 to L. You guys please try it for 5 minutes. If it is not solved, then I will proceed. Okay, let's just take 5 minutes. Okay guys, any progress? This wave function is given here, and this wave function also given. You have to just integrate. Okay, let me do this. So we have to evaluate this integral 0 to L psi n minus 1 star minus ex psi n. Okay, these are function of x, right? So this minus e is constant, I can take it out. Then this psi n minus 1 is 2 over L root over sin n minus 1 okay pi x over L. Then we have x, and see, this is a real function. If I do complex conjugation also, it won't change, right? Now we have psi n, and then we will have root over of 2 over L sin n pi x over L, right? Integration limit 0 to L. So these two are constants, I can take it out. Minus e 2 over L. Then effectively I will have x sin n minus 1 pi x over L, then sin n pi x over L. So we have three functions, and then we have to integrate. So it will be easy if we can convert these to two functions. So any suggestion, how shall we proceed from here?
Cos a minus b minus cos a plus b.
Yeah, right. This is sin a into sin b form. So 2 sin a into sin b is equal to cos a minus b minus cos a plus b, right? Good. Okay, so we have to convert this to single function. It's linear form. Then we can write this sine of n minus 1 pi x over L and sine n pi x over L as cos a minus b. This is a, this is b. Okay, so this is n minus 1 minus n, and other parts are constant, so I can write pi x over L, right? So this is cos a minus b, then minus cos a plus b. So this is n minus 1 plus n, and others are constant, pi x over L. And of course there is 2, so I have to divide it by 2, right? So okay, sorry, this is n. So you see, this n will cancel here, so effectively I will have half of cos minus pi x over L minus cos 2n minus 1 pi x over L, right? So cos of minus of theta, what I can do about it? Cos is a even or odd function?
Cos minus
What?
cos theta minus n.
Cos
Cos minus theta. Cos of minus theta means cos theta.
Yes, right. Cos theta. This is cos
Minus,
theta,
minus,
and this one
minus sin theta.
minus sin theta, because cos is a even function, and sin is a odd function, right? So this I can write half of cos pi x over L, right? Then minus cos 2n minus 1 pi x over L. Okay, so I wrote this term as this. Now apply this term in the integral. So in this integral we had minus e 2 over L integration from 0 to L x times this multiplication of sin A into sin B. So we rewrote those sin A into sin B to cos terms. So effectively we'll have half of this term. So half I can take it out, then I can write this term cos ix over L minus cos 2n minus 1 by x over L dx, right? So this 2 cancels. Now I'll have minus e over L. I'll have to do two integrations, x into cos pi x over L dx 0 to L minus x cos 2n minus 1 pi x over L dx. So how shall I proceed from this? This is I have to do integration by parts, right? So which one I have to do integrate, and which part I have to do derivative? There are two functions u and v. Which one I have to do derivative, which one I have to do integration? Any suggestions? See, this is x, right? So if I do a derivative, it will vanish on repeated derivation. Sorry, not derivation. Repeated derivative. If I do, then it will vanish eventually. But if I do derivative, it will oscillate from cos to sine, then sine to cos, right? So it will be wise if I do integration of this term and derivative of this term while applying this integration by parts. Okay, let's do this, and we'll have e by L, then this will remain as u, then this is nothing u dv, right? Then v will be integration of this cos pi x over L, right? Then this will be sin pi x over L by pi over L. Limit goes from 0 to L. Okay, then minus okay, this is equal to ub minus du integration of v. Right, then according to this formula we will have a derivative of this u, then it will be giving us 1, then integration of this dv, then it will give us b, which is sin pi x over L by pi over L. Are you getting this? I just simply applied integration by parts. Hello.
Yes, sir. We are doing. We have done also. Means I have done like that also.
Okay, then okay, good. We'll finally match our answers. Okay.
Okay.
Okay, so first term I did, then let me apply this to second term. Then this will give me cos a sorry x sine 2n minus 1 pi x over L divided by 2n minus 1 pi over L 0 to L. Then there will be minus, here is a minus, so effectively plus derivative of this x is 1, then integration of this sine 2n minus 1 pi x over L by 2n minus 1 pi by L, limit from 0 to L, right. Okay, so let's apply the limit. If I apply the upper limit L here, then this will be L sine pi, right. So sine pi is 0, so it will give me E by L. So upper limit will give me 0, then if I apply lower limit, then there is x, so this will also give me 0. So first term will give me 0, right. Then minus integration of this sine function. Okay, so let me pull out this constant first, L over pi, then integration of sine. What is the integration of sine function?
Minus cos.
Yeah, minus cos. So it will be minus minus plus here. So this is cos pi x over L by pi over L, limit from 0 to L, right. Then we have to apply the upper and lower limit here. So if I apply upper limit, then L sine of 2n minus 1 pi L by L. So this is L sine 2n minus 1 pi by 2n minus 1 pi over L. So what will be the value of this term? You already did this, right? So what will be the value of this sine 2n minus 1 pi? Okay, the lower limit will obviously give me 0. What will be the value of this?
So sine pi means it will be 0.
Right. So there is 2n minus 1. So if you put n equal to 1, 2, 3, then what you will get? You will get sine pi, 3 pi, 5 pi, the odd multiplication of this pi. Okay, so whatever it is, sine of some n pi is, it will be always 0, right. So this function will give me 0. Okay, this okay, this term is goes to 0. Then next one, let me pull out the constants. Then integration of sine will give me minus cos, so this will be minus here, cos of 2n minus 1 pi x over L by 2n minus 1 pi over L, right. Okay, then this will be effectively minus E over L. Okay, so if I apply upper limit here, then this will be giving me cos pi. What is the value of cos pi?
1, sir.
Cos pi is 1 or
Sorry,
minus 1?
minus 1.
Yeah, minus 1. Okay, let me write the constant first. L over pi, there was 1 L over pi, so it's square. So this gives me minus 1, so this minus, right? And if I apply the lower limit, 0, cos 0 is
1, sir.
1, so minus um, L over pi square, right? Then this term goes to 0. Coming to this term, let me write down the constants first. L by 2n minus 1 pi whole square. Now if I apply the upper limit, then I will get cos 2n minus 1 pi. What is the value of this? See, I have given you a hint here. If you put n values 1, 2, 3,
Minus 1, sir.
yeah, this will give me minus 1 because it will always say odd integer of pi. Then it will give me minus 1. Okay, now if I put 0, then cos 0 is 1. So this is minus of 1, right? Okay, now let's simplify this. Okay, this is minus e over l minus 2 L over pi whole square, and then this is minus 2 minus okay, there is plus, okay, yeah, correct. So this is 2 L over 2n minus 1 pi whole square. So this much you got.
No, it's something else. Okay, sir, you please carry on.
Okay, what you got, just tell. Maybe if we simplify this, then we will get that one also. What you got?
Somehow it has been one term I have cancelled, so I have to recheck it.
Okay, from these terms, one term got cancelled. Okay, there must be some plus minus mistake.
Yes, sir.
Okay, you can further simplify this. 2e over L over pi whole square minus L over 2n minus 1 pi whole square. Okay, so what is there in question? We have to find the L dependence of A and B coefficients, right? So this we are solving for this integral part. Then if we put this integral here, then we will get B value, right? These are all constants. The L dependence comes from here, so I should not bother about writing all the constants. Let's just pull out all the L's. Then we will have 2e L square. Okay, there is a L here. 1 over pi whole square minus 1 over 2n minus 1 pi whole square, right? Then there is a L denominator, numerator got cancelled. So this integral it depends, means this is proportional to L, right? Then this B is equal to some constants and mod square of this n mu dot epsilon n minus 1 mod square, right? Then this B will be proportional to L square, right? Because this integral is proportional to L and our B coefficient is proportional, equal to proportional to this integral's mod square. So this B will be proportional to L square, right? So one dependency we got, B depends on L square by, sorry, B depends on L by this relation. So halfway we covered. So B depends on L square. There are two options now. Then we have to solve for A also. Okay, what is the relation between A and B? This A by B equal to 8 pi h over CQ nu to the power 3, and we already got what is nu here. So let's put, there is no space. Okay, A by B equal to 8 pi h over CQ probably 8 pi h by CQ nu q, right? So these are all constants. Let's take it to be k. The nu value we got from here, and it depends on L square also. So these all are constants, right? I should not bother about them. So nu is proportional to 1 by L square. So this A by B will be proportional to 1 by L square cube, right? Because nu is proportional to 1 by L square, right? Then this A by B is proportional to 1 by L to the power 6, right? Then this A will be equal to some constant times B, right? So this okay. Let's not put it this way. So this A will be proportional to 1 over L to the power 6 times B, right? So B is already proportional to L square. So this A then will be proportional to 1 over L to the power 6 then L square. So this will give me 1 over L to the power 4, right? So this A is proportional to L to the power minus 4. Got it?
Yes, sir.
Okay, so let's check the options. Yeah, B is proportional to L square and A is proportional to L to the power minus 4. So this is the right answer. Right. Any doubts?
No, all right, sir.
Okay. So whatever the formula I have used, these all are taught in class. Okay, you can always go and check there. Okay. Coming to the next question. Is a mechanism for downward transition. Spontaneous emission competes with thermally stimulated emission. Okay, stimulated emission for which Planck's radiation is the source. That means some external photon will come with energy h nu, and it will stimulate the excited particle to emit some another photon to go to ground state. This is stimulated emission, right? This happens in the presence of this Planck radiation. Okay, then so that at room temperature, that means at T equal to 300 Kelvin, the thermal stimulation dominates for frequencies well above 5 into 10 to the power 12, whereas the spontaneous emission dominates for frequencies well above this. So which mechanism dominates for visible light? Okay, so first of all, this radiation is of frequency 5 into 10 to the power 12 hertz. Okay, and the temperature of this system is 300 Kelvin. So any suggestion how to proceed to this question? The hint is given, downward transition, so it will always be emission. So there will be spontaneous emission and stimulated emission. So now we
So
have
is
to
it by ratio of N1 and N2?
there is no information about N1 and N2, so you can consider N1 and N2 as one. There is one particle system. So emission is considered, right? So stimulated and spontaneous emission. So Einstein coefficient A and B will come into picture, right? Then we know from the class, for spontaneous emission, the rate will be dependent or proportional to this Einstein coefficient A for spontaneous emission. Okay, spontaneous emission, and this W will also be proportional to number of particles or number of states in this configuration. So let's say this is N2 and we have considered this to be 1. So this will only be proportional to A. So let me write the correct form. Is W spontaneous, this will be equal to 8 pi cube over 3 h cross epsilon naught c cube nu cube, and this let's say there are two states, 1 and 2, then this will be 1 mu dot epsilon 2 mod square, right? So this is the spontaneous emission rate, and there is another kind of emission can be happening because there is radiation, Planck radiation in the surrounding. So there can be stimulated emission, which I can write as pi over 6 epsilon naught h cross square, this integral, transition integral mod square times the energy density or the state density, which depends on nu. Okay, so this part I can get from Planck's radiation formula, and this actually I can evaluate, but I don't have to, because we have to show at room temperature which process will be dominating. If in room temperature the frequency is this much, then which one will dominate, this one or this one? So you must be remembering from class there was some relation A by B, this was proportional to nu cube, right? So nu is what? This is the radiation frequency. So if there are two states, 1 and 2 and energy E1 and E2, the energy gap E2 minus E1 can be written as h nu, where this h nu is the incoming radiation energy, right? So you see this energy gap is equal to this radiation energy, right? So if nu increases, the gap also increases, right? So from this relation you see, if nu increases, then A will dominate over B, right? Because let's say this A by B equal to some constant times nu cube, then A will be equal to K nu cube B. Then if nu increases, then A will be more dominant than B, right? This is pretty straightforward. Are you getting? So if the separation is more, then A will be dominating over B, where this A, it determines spontaneous emission and B determines stimulated emission. Then if the energy gap increases, then spontaneous emission will dominate over stimulated emission. This is being taught in week 4. You can verify from the videos. So I am just stating that class. Okay, so if the energy gap is increasing, then spontaneous emission will dominate over stimulated emission, right? Because it's very common sense. Like, let's say this separation is let's say some nu is some factor, let's say 4, okay, and there is another system E1 E2 where this nu is factor of 2, right? So and the Planck's radiation or the black body radiation in the surrounding have frequency near to 2, okay. So in this scenario, this photon can stimulate this excited particle to go to ground state, right? But in this scenario where this frequency is 2, which means this photon will have less energy compared to the energy difference of this system, so it won't be able to stimulate this particle to go to ground state. So in this scenario, what will be dominating? Spontaneous emission. That means in the absence of this external radiation, this excited particle will go to ground state spontaneously, okay. Did you get the analogy, or do you have any doubt?
No, sir.
So it's clear from here, if nu increases, then spontaneous emission will be dominated over stimulated emission, right? So what we have to find then? A over B ratio, right? Or this rate of transition ratio, spontaneous, this is not equal to A over B, there will be some what you call this state density will be there. So this rate of spontaneous emission divided by stimulated emission will be so did I write the formula? Yeah, we have to take the ratios between these two, okay. So you see, we don't have to evaluate this because while taking the ratio it will cancel, so we don't have to do this tedious job, okay. still let me take you stimulated in the numerator. So the stimulated emission rate is equal to pi over 6 epsilon naught h cross square. This integral mod square and this state density. Okay, this is the stimulated emission rate. Now for spontaneous emission we'll have 8 pi cube over 3 epsilon naught h cross c cube, then this integral mod square and nu cube. Okay, so from here we see we don't have to evaluate this will be automatically cancelled out, and from numerator and denominator this pi and pi cube, okay, this will cancel, 1 pi will cancel, and epsilon will cancel, 1 h also will cancel, so we will have 3, okay, 3 will also cancel, this will be 2, so we will have c cube over 2h cross 8 pi, I think, correct me if I am doing wrong, this is nu cube, and this density function we can get it from Planck's theory of black body radiation. So this is rho nu will be nothing but 8 pi h nu cube over c cube 1 over e to the power h nu kt minus 1. Okay, now we can substitute this in this equation, but you see there is h cross, and in this formula there is h, so any one of it we have to convert. So let's convert this one. So if we convert this, what is h cross? H cross
is h by 2 pi.
Yes, this is h by 2 pi. So h will be 2 pi times h cross, right? So I can substitute this h here by this 2 pi times h cross. So this will be 16 pi square h cross nu cube by c cube and this factor. Okay, so now let's substitute. This will be 16 pi square h cross nu cube by c cube times this 1 by e to the power h nu by kt minus 1. Okay, so everything should cancel now. CQ cancel, nu to the power q cancel, h cross cancel. Okay, so there is 1 pi. Okay, there was pi square here, actually pi to the power q was there, 1 pi cancel, so this should be pi square. So 8 into 2, 16 pi square, 16 pi square cancel. So effectively we have 1 over e to the power h nu over kt minus 1. So this stimulated was divided by spontaneous emission rate is this much we got. Okay, so at thermal equilibrium we are assuming that this stimulated and spontaneous emission will have same rate. Spontaneous okay, so we are assuming this. So according to this we should have this ratio to be 1, right? Now if we solve this, this should be 1, then e to the power h nu over kt minus 1 equal to 1. So e to the power h nu over kt, this is equal to 2, then h nu over kt is ln of 2, right? Then this nu, whatever we will get, this should be called as critical frequency, because let's first calculate, then I'll explain. Then this nu c will be equal to kt over h ln over 2, right? Why this is called critical frequency? If the frequency is more than this critical frequency, then we'll have this two level system. This h nu, if h nu is greater than this h nu c, then what will have, the energy difference will be more. So in that case, spontaneous emission will dominate, right? So we got some critical frequency above which, if we have the energy separation, if nu is greater than nu c, then spontaneous emission will dominate. Right, and if we have nu less than nu c, then stimulated will dominate, right? So I have already explained why this is so. So we got this nu c to be kt over h 2 ln 2, okay, and we are given that the environment or the surrounding is having photons with this frequency 5 into 10 to the power 12. So to compare it, we have to first calculate nu c numerically. So then we can check whether this radiation is more than nu c or less than nu c. Okay, so let's calculate this nu c. Do you know the value of k? This is Boltzmann constant. Do you know the value of k? If you don't know, it's
8.85 into 10 to the power 12 or something.
This is actually 1.38 into 10 to the minus 23 joule per Kelvin. This is the Boltzmann constant. You can check it in internet. Okay. Then T is given 300 Kelvin. This is 300 Kelvin. Now, do you know the Planck's constant value? Its value? This is 6.63 times 10 to the power minus 34 joule into second, right? And there is of course this ln2 factor. Can someone quickly calculate and tell me the numerical value? Okay, just I am writing the numerical value you cross check.
0.43 in 10 to the power 13.
0.43 into 10 to the power 13. And unit?
Unit. Case to the power minus 1. Kelvin second.
Here you see joule per Kelvin, and there is a Kelvin. So Kelvin will cancel,
Oh,
and joule will
then the
also
second per second.
second inverse. Or this is frequency, right? So what is the other unit?
Frequency means hertz.
Yeah, right. So this is 0.43 into 10 to the power 13 hertz. Okay, let me rewrite this 4.3 into 10 to the power 12 hertz. Okay, so critical frequency is 4.3 into 10 to the 12 hertz. So if we have frequency more than this, then in that case spontaneous emission will dominate, right? So what is the radiation frequency we have 5 into 10 to the 12 hertz. So obviously we have more than 5 into 10 to the 12 hertz, more than this critical frequency, right? So in this case what will dominate?
Spontaneous.
Yeah, spontaneous emission will dominate. Okay. To stimulated emission be dominated, what should be the frequency? What should be the frequency so that the stimulated emission
Less than 4.3 into 10 to the power.
Yes, right. It should be less than 4.2 4.3 into 10 to the 12 hertz, right? So we got the answer. This in this environment spontaneous emission will dominate. Okay, so there is another question also. So which mechanism will dominate for visible light? So do you know the frequency for visible light? Some range are there for visible light. It's of the order of 10 to the power 14. Okay, so it's obviously greater than critical frequency. So in this case, in the presence of this visible light, then what will dominate? The spontaneous emission, right? Understood?
Yes, sir.
Okay. Any questions so far? Okay. So we'll move to next question. Okay. So what is electric dipole transition? This is just general question. There is no option.
It's mod square of this state change of one state to another. No,
Yeah. So what is this operator?
mu and epsilon e.
Yes. What is this epsilon?
Unit vector.
Unit vector of what?
Electric field.
Yes, right. Electric field. And this mu, what is this?
Permittivity.
No,
No, mobility.
no. Actually, there are two molecules A and B separated by some distance r. Let's say this is positive, then this is negative. There is some quantity we can define for this kind of system. What we call this kind of system? Plus minus separated by some distance. This is a dipole, right? some plus and minus charge separated by some distance. This is called a dipole. And if there is a dipole, then there will be some dipole moment going from plus to minus. So this mu is nothing but dipole moment, which will be equal to charge times the distance separated. Right. The charge, if we consider E or minus E, if it is an electron, and the separated distance is r, then this mu is this minus E times r. This is dipole moment. Right. So this is electric dipole moment. It can interact with electric field. See, so if there is some electric field and we have this dipole aligned like this theta, let's say this direction is mu, then there will be some interaction between this dipole moment. Actually in electrodynamics it is represented as P for electric dipole and mu is for magnetic dipole. Okay, so just take it as electric dipole, this mu. If there is magnetic field, then this mu will be magnetic dipole. Right. Here we have considered electric, so this is electric dipole. So if there is electric dipole moment in the electric field, their interaction will be mu times E dot product. So this is nothing but mu magnitude times E's magnitude cos of theta, where theta is the angle between this electric dipole and external electric field. Right. Similarly, if you have magnetic dipole mu and there is external magnetic field, the interaction term will be mu times B. Right. So this dipole transition is this integral form. Here actually I have given the answer. So electric dipole transition takes place when one oscillating electric field interacts with the electric dipole moment minus ER of an electron inside an atom. So if we have some radiation, let's say some photon which is traveling in this z direction, let's say, then where this electric field will oscillate in perpendicular to this z direction, let's say this is x direction. Right. So there will be some oscillation of electric field perpendicular to the direction of motion of this radiation. Right. So if we have a dipole with dipole moment, let's say P, I am denoting this P, then their interaction, this interaction of this electric field of this radiation with this dipole moment is called dipole transition. When this interaction will make result a transition between two states, then this process will be called electric dipole transition. Okay. So if you have electric field, then you will have magnetic field also. This magnetic field will be perpendicular to both electric field if this is electric field, then there will be magnetic field which will be perpendicular to both electric field and the direction of propagation. Right. So if we have magnetic field and if we have some magnetic moment, let's say there is a positive charge and some hydrogen, let's say proton is there and one electron is revolving around it. So the revolution of electron will induce a current. So effectively you will have magnetic moment also. So if you have magnetic moment in the presence of this radiation, then also you will have interaction of this magnetic field, magnetic moment with this magnetic field, right? So it's just a dot product, mu dot B or P dot E. Electric dipole will interact with electric field, magnetic dipole will interact with magnetic field. Okay, so this radiation is always oscillating, obviously, because this is radiation. Oscillating electric field will induce oscillating magnetic field, and this oscillating magnetic field will induce oscillating electric field. That's how this radiation propagates. Okay, so this radiation can interact with this kind of system where there will be some induced magnetic field or some charge cloud separation between this positive charge, let's say, and negative charge, so which will induce some electric dipole moment. So in that case also this radiation can interact with this system. Okay, so any doubts on this in questions? Did you understand what I told here? I guess you all are familiar with electric dipole moment. Magnetic dipole moment maybe you will study in future, because moving current will induce magnetic moment, so we will study about this. So for our course we will stick with electric dipole transition. What is this? The interaction
So
between,
that means state transition is also electric dipole transition.
yeah, this state transition, this can if there is some external electric field, oscillating electric field, it will interact with this dipole, and it will absorb or make it radiate some energy, and it will make it to change its state. Like initially, let's say there is a positive charge and this electron is revolving around this first orbit n equal to 1, and there is second orbit n equal to 2. This radiation, this photon, will interact with this system. Let's say this is plus and this is minus. So effectively there is a dipole moment, right? So this oscillating electric field or this radiation will interact with this dipole moment, and it will change its state. Let's say this electron will jump to this state, right? Then in that case r will change, so momentum will change, because it will absorb this energy, so its momentum will change, right? This is called electric dipole transition, right?
Right.
Okay. Okay, so here I have given some illustration. What is absorption, spontaneous emission, and stimulated emission. So here in the first case you can see this is a two level system, and the particle is in the ground state, and there is radiation coming. So this particle will absorb this radiation or this photon, then it will jump to the excited state. So this is called absorption, photon absorption. Okay, so in next case, let's say there is no radiation in the surrounding. The system is isolated, that means it's in a dark room. So in that case what can happen, this particle can radiate this photon and go to ground state. So this kind of situation is called spontaneous emission. So there is nothing to stimulate this process, it will spontaneously go to the ground state and will emit one photon. So this is spontaneous emission. Now in third case, there is a radiation background, so this radiation will come and this will stimulate this electron in excited state and make it jump to the ground state. So the jumping of this particle to ground state will emit one photon, and there is already one photon which is stimulating this process, so there will be two photons outgoing for this stimulated emission. So this is the difference between these three processes. Okay, any questions on this? Okay, I guess no. Then we will move on to the next question. Okay, which of the following is the correct expression for the relation between Einstein coefficient A and B? That means you are asked what is the ratio between A and B. Which of the relation is correct? Just ask.
The first one.
Yeah, right. This A over B will be proportional to this nu q. So if you are clever, you can identify this first one will only have this nu cube. So right, good. What is the relation between B21 and B12? One is related to absorption, one is related to stimulated emission. So what is the relation between these two? So let me give some condition in thermal equilibrium. Okay, no, thermal equilibrium is not needed. What is the relation between these two?
It's equal, no, sir?
Yeah, right. This should be equal. Few slides back I told you, right? There is some photon coming h nu. Let's say there is a particle, it will absorb this photon and it will go to the excited state, right? This is called absorption, right? In the second state, this particle is there and one photon is coming, let's say h nu. It is stimulating this particle to go to ground state, so it will emit h nu. Okay, so in both the cases the energy difference is h nu. So in this scenario, both the coefficient B12 and B21, they are emitting same energy, right? So the coefficient should be equal, right? C is the right answer. Okay, which law is used for achieving the relation between Einstein coefficients?
Planck's radiation law.
Yes, correct. We are using this density function which is proportional to this nu q, and our A by B ratio is also proportional to nu q. So we are using this Planck's radiation law to achieve this relation, A by B ratio. Okay, good. The probability of spontaneous emission increases rapidly with energy difference between the two states.
Right, sir.
Yes, because few slides back we discussed this. If the energy difference is more than A by B ratio, which depends on nu q, this h nu is the energy difference, If energy difference is more, then nu is more, then A is related to spontaneous emission, B is related to stimulated emission or absorption. Okay, so if this nu increases, then spontaneous emission will dominate over this stimulated emission, right? So this should be true. Okay, good. Okay, if the frequency of emitted photon is 10 hertz, the ratio of Einstein's coefficient is, okay, so emitted frequency is 10 hertz, so this nu is 10 hertz, and you are asked this A by B ratio. Okay, you might not remember this one. Let me tell you, A by B ratio is 8 pi h over cq nu q. So everything is given, just calculate and tell me the answer. C you take 3 into 10 to the power 8 meter per second. H value you know, Planck's constant, pi is a constant, everything is given, just calculate and tell me the value.
Sir, H was how much? 6 point something.
Okay, H value is 6.63 times 10 to the power
6.
minus 34 joule into second.
Sir, option C.
Option C, no, the answer is D. Let's check. 8 into 3.14 times 6.63 times 10 to the power minus 34, 3 cube, 10 to the power 8 cube is 24, and this new value is 10 hertz, so 10 to the power 3. So this is 27, and this, if you calculate, you will get actually 6.177. You put it in calculator and check. The answer should be D. Okay, so you check it. Coming to the next question, what is the unit of the coefficient spontaneous emission? What is the unit of A? See, the rate of spontaneous emission is equal to A times N, right? And this rate is nothing but the number of particles emitting per time. So yeah, its unit is second inverse, and here n is dimensionless, so A should be second inverse. So A should be the right answer. Right. So you just check the lectures. This should be some probability divided by time. So probability is unitless. So time you have second. So it should be second inverse. So if left hand side is second inverse, right hand side should be second inverse also. Okay. Any doubts?
No.
Okay. Okay. Which Einstein coefficient should be used in this case? Okay, there is a picture. You check it and tell me which Einstein coefficient should be used here and what kind of process is this.
Sir, B21.
Yes, right. And what kind of process is this?
Spontaneous emission.
Spontaneous.
Oh, sorry, stimulated emission.
Yes, it is stimulated by this H nu. So this is stimulated
Absorption
emission.
opposite stimulated.
Yeah. This particle is going to ground state and radiating one photon. So this is emission, and this is stimulated by this H nu. So stimulated emission. So B21. Good. Okay. What is the unit of coefficient of stimulated emission? So few slides back we wrote the rate of stimulated emission. It was equal to some, okay, I didn't write in terms of B. Okay, let me write it in terms of B21 N2 times the density function. Okay, so this is emission, right? So it should be directly proportional to the number of particles in this state 2, and this density of radiation in the surrounding, right? So the formula is like this. So here this is dimensionless, this has a dimension second inverse, this is radiation density, which you can get from Planck's radiation formula, 8 h over c cube mu cube. Okay, what should be the unit of this? This is joule second, this is second to the power minus 3 because cube is there, this is meter per second, sorry, meter per second cube. So meter cube second to the power minus 3, and in the numerator second, joule into second. So second to the power minus 3, second to the power minus. Okay, let me check, verify did I write the correct form. Yeah, okay, some constant is there, 1 over e to the power minus 1. So these are dimensionless, so doesn't matter. So we have joule second by meter cube for this row. Okay, so this its dimension is joule into second per meter cube, and here this quantity B21, and in left hand side we have second inverse. Okay, so this B21 dimension should be joule inverse meter cube second to the power minus 2, right? So D should be the right answer. Okay, understood?
Right, right.
Okay. An ensemble of 10 to the power 5 identical atoms in an excited state, then Einstein coefficient A, whose value is this, then calculate the rate of spontaneous emission. So this spontaneous emission, this is equal to A times N, right? And N is given, A is also given, and then you have to just multiply and calculate the number. This the A is 2 times 10 to the power 7, and this N is 10 to the power 5. So this is 2 into 10 to the power 12 second inverse, right? So this is the answer. This is spontaneous emission rate. Okay, so this is the last question, I think. Okay, certain radioactive isotope undergoes spontaneous decay with half lifetime T half 10 days. Calculate the rate of spontaneous emission for this isotope in decays per second. Okay, so T half is given in 10 days. So in 10 days, this isotopes goes to number half. So let's say this initial number was N. So in this time T, the isotope number will go to N over 2, or you can picture this as in this second state there are N number of particles initially, or you say there was one particle in this second state initially, and it will decay to first state by this spontaneous emission, and there are N such particles. Okay, so what is given? This T half is given 10 days. So in this time period, the number of particles which are in this excited state, they will go to, means half of them will go to ground state. Okay, so this rate dN over dt for spontaneous emission, what is this? This is N times A, right? Now if I solve this equation, this has already been solved in class, so you will get N0 e to the power minus 80. So if you compare with decay formula, this A is nothing but decay constant. From nuclear physics class you might be recognizing this as lambda. Okay, so in this time T half, this N goes to half number. Okay, so this N of T, okay, let's write this as N of T half over N of 0. This is e to the power minus 80 lambda, whatever you can write. Okay, so this goes to half, so this number is half. Okay, so minus a T half is ln of half or minus ln of 2. Okay, so this A should be ln of 2 by T half. So you will get the value of A from here. First you have to convert this to seconds, and this one is constant. This value you will get 2 over 10 into 24 into 60 into 60. This will be in second. So once you got this A value, then you can calculate this rate, right? Minus dN over dt. This is A times N. So So if you get a from here and n you already have, you just multiply and you will get this value. Okay, you try this, and time is over for today. So any questions on this problem?
Sir, in how much you will consider here? 1.
Okay, okay, n is not given. So okay, let's consider n is 1 or 1 mole. You consider whatever it is. So if you consider n equal to 1 mole, then it will be Avogadro's number 6 point something into 10 to the power 23. Okay, you just consider Avogadro's number also. That will be fine. Or you consider 1, but for 1 there is no meaning of this half lifetime, so you consider 1 mole. Okay, so you understood the question, right?
Yes, yes. Thank you.
Okay, so there are no more questions, so we will stop here. See you in the next class.
Okay. Good night, sir.
Good night.